Good evening, guys. This is Yeshwan Nagendra Reddy, pursuing BTech second year in the branch of ECE VVIT University. I am here to represent my seminar topic on the power spectral density in the probability theory and stochastic process. First, we have to know the definition about the cross power spectral density. It tells you at what frequencies the two random variables share the common power. The cross power spectral density, it means it is the complete in the frequency domain. It tells at what frequency the both random process is going to share the common power, and how strongly they are related at each frequency. Next, their phase relation at each frequency. It represents with sxy of f at equal to 0 at some frequency. They are not related at that frequency. And the definition is, let us consider two random variables, that is x of t and another one is y of t. They both are widely jointly weights and stationary random process. If the two random process have the conditions for the two random process to be weights and stationary means it constant, it mean must be constant, and the autocorrelation depends on the uh, difference of the times, not on the absolute time. Then the cross power spectral density is defined as the Fourier transform of the cross correlation function x of t and y of t. If you apply the Fourier transform to the if you apply the cross correlation function of x of t and y of t, that cross correlation function I have to apply Fourier transform, then we get the cross power spectral density. For cross power spectral density means it cross correlation means one random variable with respect to x, another random process with respect to y. It represents with sxy of omega. The definition, the formula for the cross power spectral density is integral minus infinity to infinity rxy of tau e power minus j omega t tau. Here what we are doing means we are applying the Fourier transform for the cross correlation functions of x of t and y of t with respect to tau. Tau means your time difference. Time difference means the x, the random process x held at the time t1 and the y at time t2, and also it can be vice versa, and also it can be written as vice versa, like sxy of omega is equal to integral minus infinity to infinity ryx of tau e power minus j omega d tau. By inverse Fourier transform we can obtain the cross correlation functions. Let us apply, let me apply inverse Fourier transform for the cross correlation functions. We can obtain the cross correlation function rxy of tau is equal to 1 by 2 pi 1 by 2 pi integral minus infinity to infinity sxy of omega into e power j omega t d omega. If we get the power spectral density in terms of frequency, we are applying the Fourier transform for the cross correlation function. If we apply cross correlation functions to the if we apply Fourier transform to the cross correlation function, we get the power spectral density. When we apply Fourier transform, if we apply inverse Fourier transform, we get the cross correlation functions. When we apply the inverse Fourier transform to the power spectral density, these both are vice versa. Therefore, cross power spectral density and uh, cross correlation functions are Fourier transform pairs. But let us consider two signals that are x of t and another one two random process, or it can call as random process. For two signals or two process, it is called they are x of t and y of t. Cross power spectral density denoted as xxy of f. Here f means frequency. The both random process here x of t and y of t in terms of frequency the is the Fourier transform of the cross correlation function between x of t and y of t. Sxy of omega is equal to Fourier transform of cross correlation function with respect to time, whereas rxy is equal to cross correlation between x of t and y of t. Here f represents Fourier transform. And let us see properties of the cross power density spectrum. First property is Sxy of omega is equal to Syx of minus y Syx of minus omega. If we apply a if we apply a conjugate term of the frequency term in the power spectral density, we get the same conjugate is equal to imaginary part is equal to real part. Consider the cross correlation functions Rxy of tau, the cross power spectral density. Sy, we know that this is a proof for the above property. Sxy of omega is equal to integral minus infinity to infinity Rxy of. Here what we are doing means applying the we are applying the Fourier transform for the uh, cross correlation function. Let tau is equal to minus tau. We are replacing the tau with minus tau. Then then here we are Sx next Syx of omega is equal to integral minus infinity to infinity. These both are vice versa. Next conjugate symmetry. If x of t and y of t are two real signals, here what we are doing, Sxy of minus f is equal to Syx of f. Similarly, and also Sxy of minus f is equal to S conjugate Sxy of this means negative frequency part is mirror of positive part. Linearity property. Let us consider two signals or two random process x1 of t and x2 of t and a constant a, and a is a constant. Let us consider in terms of s of ax plus y ax of f, ax of sx of f plus as yx of f. This property allows the combining spectra of multiple signals. Relationship to the auto power spectrum. When both signals are same. Here we are taking the signals x and another signal also x. Both signals are same. So then we can represent as sx of f is equal to sx of f into x conjugate of f. Here x is the real part. This is conjugate term. X is the real term. This is the conjugate term. So CSP becomes auto power spectral density. Next, Sxy of omega is equal to 0. Syx of omega to 0. If both 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 process x of t and y of t is said to be orthogonal, means the cross power spectral density must be 0. Let us see and let's see the proof. From the properties cross correlation function, we know the random process x of t and y of t are said to be orthogonal, and if and only if their cross correlation function is 0. If we want if both these random processes are said to be orthogonal, the PSD must be 0. That is Rxy of tau is equal to Ryx of tau is equal to 0. We know that Sxy of omega is equal to integral minus infinity to infinity Rxy of tau is equal to e power minus j omega d tau. Here we know, here if you want to, if you said both these random processes is said to be PSD, we have to equal the PSD equal to 0. Next, Sxy of omega is equal to Fourier transform of a into Rxy of t comma t plus tau, and Sxy of omega is equal to Fourier transform of a into Rxy of t comma t plus tau. Also, if x of t and y of t are jointly wide set stationary random process, then Sxy of omega is equal to Fourier transform of Rxy of tau, and it is similar to another one also, Syx of omega is equal to Fourier transform of this autocorrelation function. Consider x of t and y of t are two random process. Let xt of t and yt of t are defined in terms of xt of omega is equal to integral minus infinity to infinity x of t into e power minus j omega dt. It is similar to Fourier series. This x, if you apply Fourier series to the this random process, we get the this xt of omega in terms of frequency. Xt of omega is equal to xt of omega into yt of omega is equal to, we are splitting these two random process in terms of 2, means we are multiplying these two frequency components from the equation. Sxy of omega Sxy of omega is equal to limit t tends to infinity expectation of this conjugate term into y term divided by 2t, limit t tends to infinity 1 by 2t expectation of integral minus infinity to infinity xt of e power j omega t dt integral minus t to t y of t1 e power minus j omega 1 d1. Like this, if we derive this, we can get the final this term as xy of omega is equal to Fourier transform of a into rxy of t comma t plus 2. This this is the derivation. This is the derivative part for the Fourier transform of sxy of Fourier transform of a into rxy of t comma t plus 2. A into rxy of t comma t plus 2 is equal to rxy of tau. C. If you apply inverse Fourier transform, if you apply inverse Fourier transform for the PSD, we get the cross correlation function. These two are similar, but we are interchanging the random process inside the function. These two are the converse of the PSDs. Let's see one problem. Two signals are given. X of t is equal to 5 cos 2 pi ft 250t, y of t is equal to 10 cos 2 pi 50t plus 5 by 4. Find the cross power spectral density of Sxy of f. Find the Fourier transform for this. Find the Fourier transform for this function. The Fourier transform is a into e power minus j omega del of f minus f naught plus a by 2 e power minus j phi del of f plus f x of t, and we are applying this in the before formula. X of f is equal to 25 del of f minus 50 plus 25 del of f plus 50. If you do problem and then solve it, we get the PSD like 12.5 into e power minus j pi by 4 del of f minus 50 plus 12.5 into e power j pi by 4 del of f plus 50. Thank you. This is all about power spectral density.